Welcome to one of the most powerful concepts in all of statistics and machine learning. The normal distribution. You might know it as the famous bell curve. From measuring human heights to modeling stock returns. From quality control on factory floors to training deep neural networks. The normal distribution is everywhere. In this video we will explore what makes it so special. Its elegant bell shape. The remarkable empirical rule, Z-scores, and why virtually every machine learning algorithm makes assumptions rooted in this single distribution. A normal distribution is a continuous probability distribution that is perfectly symmetric around its mean. The shape it creates, that iconic bell curve, is described by a single elegant equation called the probability density function, or PDF. In this formula, mu is the mean, the center of the bell, and sigma is the standard deviation, controlling how wide or narrow the bell is. E is Euler's number, approximately 2.718, and pi is the familiar 3.14159. Together they produce a smooth, symmetric, infinitely extending curve that sums to exactly 1. Here is the standard normal distribution with mean 0 and standard deviation 1. Notice how the curve is perfectly symmetric around the red vertical line at the mean. The curve rises smoothly from both sides, reaches its peak exactly at the mean, and then falls away gently toward the tails, never actually touching the x-axis. This property, called asymptotic behavior, means that theoretically any value is possible, but extreme values become vanishingly rare. The total area under the entire curve always equals exactly 1, representing 100% probability. The standard deviation sigma is the most important parameter shaping the bell. A small sigma of 0.5, shown in green, produces a tall, narrow bell. Data is tightly clustered around the mean with little variability. The standard curve with sigma equals 1 is our baseline in teal. A large sigma of 2.0, shown in purple, produces a short, wide bell. Data is highly spread out. Crucially, no matter how wide or narrow, all three curves still have the same area of 1 underneath. The shape changes. The total probability never does. Let's solidify 5 fundamental properties that define every normal distribution. First, perfect symmetry. The left half is a mirror image of the right. Always. Second, the mean, median, and mode are all identical and located at the center. This is unique to symmetric distributions and simplifies analysis enormously. Third, the distribution is unimodal, one single peak at the mean. Fourth, asymptotic tails. The curve glides toward but never reaches 0, meaning extreme events are possible but exponentially rare. Fifth, the total probability is exactly 1. The area under the entire curve. A mathematical certainty that your data point falls somewhere on the curve. Now we arrive at the crown jewel of the normal distribution. The empirical rule, sometimes called the 3 sigma rule. Within one standard deviation of the mean, between mu minus sigma and mu plus sigma, lies exactly 68.27% of all data. This is the blue shaded region you can see right now. For human heights with mean 170 centimeters and sigma 10 centimeters, 68% of people fall between 160 and 180 centimeters. Within 2 standard deviations, shown in green, we capture 95.45% of all data. Only about 4.55% of observations fall in the two outer tails combined. This is why the 95% confidence interval is so widely used in statistics. It maps directly to two standard deviations in a normal distribution. In our height example, 95% of people are between 150 and 190 centimeters. Within three standard deviations, shown in red, lies 99.73% of all data. Only 0.27%, roughly 1 in 370 observations, falls beyond 3 sigma. This is the basis for 6 sigma quality control programs in manufacturing, where the goal is to push defect rates beyond 6 standard deviations, achieving fewer than 3.4 defects per million opportunities. This tiny outer region is what we call a statistical anomaly or rare event. Here's a quick reference table for the empirical rule. 1 sigma covers 68.27%, leaving 31.73% in the tails. 2 sigma covers 95.45%, leaving only 4.55%. 3 sigma covers 99.73%, leaving just 0.27%. Memorize these three numbers: 68, 95, and 99.7. And you will unlock instant intuition for almost every probability problem involving the normal distribution. The Z-score is the magic key that lets you compare observations from completely different normal distributions on the same scale. The formula is simple. Z equals x minus mu, divided by sigma. Subtract the mean, then divide by the standard deviation. A Z-score of 0 means you are exactly at the mean. A Z-score of +1 means you are 1 standard deviation above the mean. A Z-score of -2 means you are 2 standard deviations below. Z-scores are dimensionless. They work regardless of the original units. Let's walk through a concrete example. The class mean is 70 and sigma is 10. Student A scored 85, Z equals 85 minus 70. Divided by 10, giving plus 1.5. Student B scored 55, Z equals 55 minus 70. Divided by 10, giving minus 1.5. Student A is 1.5 standard deviations above the mean. Looking up this Z-score tells us they scored better than 93% of the class. Student B is 1.5 standard deviations below. They only outperformed 7% of peers. The beauty of Z-scores is that you can compare results across different tests, different years, or even completely different subjects using this single standardized scale. The normal distribution isn't just theoretical. It appears constantly in the real world. Human heights follow a normal distribution. Mean around 170 centimeters. Sigma 10 centimeters. IQ scores are specifically designed to be normally distributed with mean 100 and sigma 15. Blood pressure measurements across a healthy population cluster normally, helping doctors define what normal range means. In manufacturing, the diameters of machined parts follow a normal distribution, enabling statistical quality control. Daily stock returns are approximately normally distributed. Sigma becomes the financial measure of risk called volatility. And in science, measurement errors from instruments are nearly always normally distributed due to many independent small error sources combining. This brings us to arguably the most important theorem in all of statistics. The Central Limit Theorem. It states that when you take a sufficiently large sample from any population, it could be uniformly distributed, heavily skewed, Even bimodal. The distribution of the sample means will approach a normal distribution. The formula shows that those sample means are distributed normally around the population mean, with a variance of sigma squared divided by n. As the sample size n increases, the approximation becomes better and better. This is why the normal distribution dominates statistics. It naturally emerges from averaging, making hypothesis tests and confidence intervals universally applicable across almost any domain. Now let's see why this is labeled critical for machine learning. Linear regression fundamentally assumes that the residuals, the differences between predicted and actual values, follow a normal distribution with mean 0. Violating this assumption can invalidate your entire model's statistical inferences. Logistic regression converges faster and more reliably when input features are normalized. Gaussian naive Bayes explicitly assumes each feature is normally distributed per class. Neural network weight initialization often uses a normal distribution. Techniques like Xavier and He initialization draw weights from carefully scaled Gaussians to prevent vanishing and exploding gradients. Principal component analysis assumes normally distributed data to maximize meaningful variance. Anomaly detection systems flag points beyond 2 or 3 standard deviations as outliers. Bayesian methods love Gaussian priors because they are mathematically conjugate. The posterior stays Gaussian, making updates analytically tractable. And standard scalar in scikit-learn literally converts features to z-scores, centering them to mean 0 and unit variance. Not all data follows the normal distribution, and recognizing when it doesn't is equally important. Right-skewed distributions have a long tail stretching to the right. Income is the classic example. Most people earn moderate amounts, but a few billionaires drag the mean far above the median. House prices, insurance claims, and social media follower counts all follow this pattern. Left-skewed distributions have their tail on the left side. This appears in exam scores for very easy tests. Most students score high, with a few struggling students pulling the mean down. When you encounter skewed data in machine learning, applying a log transformation or Box-Cox transformation can often restore normality, satisfying the normality assumptions your algorithms require. Before assuming normality in your data, always verify it. Start with a histogram or density plot. A quick visual inspection for the characteristic bell shape. Then use a QQ plot. If your data is normal, points should fall along a straight diagonal line. Any curved pattern signals deviation from normality. For small samples under 50 observations, the Shapiro-Wilk test is the gold standard statistical test. A p-value above 0.05 means you fail to reject normality. For larger samples, the Kolmogorov-Smirnov test compares your empirical distribution to the theoretical normal. Finally, check skewness and kurtosis numerically. A normal distribution has skewness near 0 and kurtosis near 3. Large deviations from these values warn you of departures from normality. Let's apply everything we've learned to a real quality control problem. A factory produces bolts with mean diameter 10 mm and standard deviation 0.05 mm. The acceptable range is 9.90 to 10.10 mm. What fraction of bolts pass inspection? Step 1. Compute the z-score for the lower bound. 9.90 minus 10.00 divided by 0.05 equals negative 2.0. Step 2. The upper bound gives z equals positive 2.0 by symmetry. Step 3. We're asking for the area between z equals -2 and +2. The empirical rule tells us this is 95.45%. So 95.45% of bolts pass inspection. But that still means 4.55%. Or 45,500 defects per million. The engineering solution? Tighten the manufacturing process to reduce sigma to 0.025 mm. Now the spec limits sit at plus or minus 4 sigma, giving us 99.994% acceptable bolts. Only 60 defects per million. This is the power of understanding and controlling normal distributions. Let's bring everything together in one reference table. The probability density function defines the bell curve's exact shape. The z-score formula standardizes any normally distributed observation. The three empirical rule values, 68, 95, and 99.7%, give you instant probability estimates within 1, 2, and 3 standard deviations. And the central limit theorem guarantees that sample means follow a normal distribution, forming the foundation of statistical inference. Master these 6 concepts and you have a complete toolkit for working with normal distributions in statistics, data science, and machine learning. Here are the 10 key takeaways from our deep dive into the normal distribution. It is fully defined by just the mean and standard deviation. Beautifully simple. The 6, 8, 9, 5, 9, 9.7 rule gives instant probability estimates without tables or calculators. Z-scores unlock comparisons across completely different contexts and units. The alignment of mean, median, and mode signals true symmetry in your data. The central limit theorem makes normal distribution universally relevant for averages. Machine learning algorithms make normality assumptions you should always be aware of. Always verify normality with QQ plots or statistical tests before assuming it. Log transformation and box calcs are your friends when data is skewed. Standard deviation quantifies risk, spread, and uncertainty across every field. And finally, respect the tails. A 3 sigma event happens roughly once in 370 observations. Ignoring rare events has caused real financial and engineering disasters. Congratulations! You've now mastered the normal distribution. You understand the bell curve, the empirical rule, z-scores, the central limit theorem, and how all of these connect to machine learning. The normal distribution is truly the language of uncertainty, a mathematical tool that turns unpredictable real-world variation into something precise, measurable, and actionable. Thank you for watching. Subscribe for more in-depth explorations of statistics and machine learning fundamentals. Subscribe for more statistics and machine learning content. We have deep dives into hypothesis testing, Bayesian statistics, linear algebra for milliliter, and much more coming up. Hit the like button if this helped. And drop a comment with the topic you want covered next.